In this video, we will show experimental demonstration of mesh analysis. To demonstrate the correctness of the results that we obtained from mesh analysis, we will construct this simple circuit with two different meshes, and the mesh currents are IA and IB. To keep things simple, I have chosen three different resistors, R1, R2, and R3, but all of them are 1 kilo ohm, which means they are 1000 ohms resistance. And I will construct this circuit with the three resistors shown, and for the voltage supply, I will use a voltage power supply with 10 volts. After applying KVL to the two meshes, where I have assumed mesh current IA in the left mesh and mesh current IB in the right mesh. After applying KVL in the two meshes, we get the two equations that are shown here as equation 1 and 2. And after solving these two simultaneous equations, we find that the two mesh currents are 6.66 milliamperes and 3.33 milliamperes. So in the left mesh, we have a larger current of 6.66 milliamperes, and in the right mesh, we have a smaller current. Now, the current that is coming out of the supply is equal to IA, as you can see in the figure, and this current is 6.66 milliampere. Now you can imagine that this current will flow in the resistor R1, and it will cause a voltage drop of V1. As we have written over here, V1 is equal to 6.66 volts. So this means the 10 volts at the supply positive terminal, 6.66 will drop, and the remaining 3.33 will be available at the node where R1, R2, and R3 are connected together. Similarly, the current in resistor R3 is equal to 3.33 milliamperes. Therefore, the voltage across resistor R3 is 3.33 milliamperes times 1 kilo ohms, which is 3.33 volts. The current in R2 is equal to IA minus IB, which is 6.66 minus 3.33, and therefore it is also 3.33. So in effect, what you see that the current 6.66 milliamperes is delivered by the supply, and then it divides into two equal parts. 3.33 goes and flow in resistor R2, and 3.33 milliamp goes and flow in resistor R3. And the reason why they split equally is because R2 and R3 are equal in resistance. So now let's see what do we get experimentally. As we can see that we have applied 10 volts from our power supply. So this red wire is the positive terminal of the supply, and it is connected to this resistor R1. R1 on the other side is connected to resistor R2 and R3. Both of these resistors are also 1 kilo ohm. And R3 from this point is just using a copper wire is connected to the other side of R2 as shown in the circuit, and this black wire is the negative terminal of the supply. So this represents the circuit that we have drawn over on the right side. Now let's see the voltages. We will use the multimeter for this experiment, and I have connected the multimeter to the DC voltage settings. So first of all, I want to see if my supply is actually giving me 10 volts. So I will connect with the multimeter the negative and the positive terminal to the supply, and you can see that we have 10.16 volts, so approximately 10 volts from the power supply. Now, according to mesh analysis, we found that the voltage drop across resistor R1 should be 6.6 volt, which means the voltage drop from this point to this point, so the two sides of this resistor, and I can see a voltage of 6.76, which is very close to what we calculated. Similarly, the voltage drop across R3, which is this resistor over here, it should be equal to 3.33 volts. So let's see that one. And this is 3.4. I'm getting 3.4 over here, which is again close to what we calculated. And finally, the voltage drop across R2. As you can see in the circuit, R2 and R3 are connected in parallel, so therefore they should have the same voltage drop. But in any case, we can measure that, and the voltage across here is also 3.42 and 3.42. So the two resistors have equal voltage. And now we can also verify that the KVL is satisfied in both meshes. So this actually represents our first mesh, and this is our second mesh. In the first mesh, we have 10-volt rise because of the power supply. Then we have 6.6 volts drop and 3.3 volts drop. So that makes it a total of 10 volts. On the other hand, we have 3.3 volt rise and then 3.3 volts drop. So KVL is satisfied in both meshes. One more thing that I want to discuss here is the current that is flowing from the supply. And this power supply can give me the current value in milliamperes, and it shows right now that the current is 6 milliampere. It should be actually 6.6 milliamperes, but the power supply cannot show into the decimal places. So therefore, it is very close to 6.6 milliampere. The other thing, that the voltages that we calculated and the voltages that we measured, they were slightly different. And the reason for this difference is, there are a few reasons. First of all, our supply voltage is not exactly 10 volts. Secondly, these resistances, they are not exactly 1 kilo ohm. When you manufacture resistances, they can never be made, all of them, exactly the same value. So sometimes you will see that a resistance will be a little more than 1 kilo or a little less than 1 kilo. So let's say, for example, in this circuit, if I want to see how much is the value of R3. So I will take out R3. I will put the meter into the ohm meter setting, and then I will measure the resistance between these two terminals, and that is 990 ohms. As you can see, 0.990 kilo ohms, so that is 990. So this resistor is not exactly 1000 ohms. So all these three resistors, they have slightly different values, and because of that, our experimental values will always be slightly off. But the theoretical values are correct and exact, and it gives us a method to design our circuit properly. I hope you enjoyed today's video, and that's it for today. I'll see you next time. Bye for now.